Hello and welcome to this video about electrical potential energy. In this video we're going to look at what electrical potential energy is and some ways to calculate it. So electrical potential energy is simply potential energy associated with an object due to its position relative to a source of electric force. It's kind of similar to gravitational potential energy, but the difference being that gravitational potential energy results from the interaction of two objects' masses, not their charges. So with electrical potential energy, it has to do with their charges. It's also a form of mechanical energy. So whenever we have gravitational force and elastic force and electric force acting on an object, we could write the equation for mechanical energy to include all of those different forms of potential energy. Keep in mind that anytime a charge moves because of an electric force, work is being done on that charge. Here is our little picture of this plasma sphere. As these charges move, the electrical potential energy decreases, just like gravitational potential energy decreases as an object falls. So that brings us to our equation for potential energy. And for electric potential energy, it's the change or the difference in that energy that's physically important, right there. So if we simply write this expression so that it's the distance in the direction of the field from point zero or some zero level, we can simply simplify that equation to be this. And you can see that electric potential energy depends on several things. The charge, it also depends on the electric field strength, and it depends on that displacement from that reference point in the direction of the field. The SI unit for electrical potential energy, like for all energy, is the joule. You can see that this equation is valid if we are talking about a single point charge. What if a second charge is placed nearby? We have to account for that in our potential energy, and so there's actually a different equation that we're going to use if we have a pair of charges involved. That would be this equation. Electric potential energy for a pair of charges is equal to the Coulomb constant times the charge on for each of the charges, divided by simply the distance, not the distance squared. This should look a whole lot like Coulomb's law, but Coulomb's law has r squared on the bottom. Couple of things to note about this equation. One, remember what our Coulomb constant is. It's that same number that we've been using. And also, we're assuming that the reference point for the potential electric energy is at infinity. And just to think about that mathematically, if that helps you, the electrical potential energy goes to zero as r, the distance between the charges, goes to infinity. As this gets larger and larger and larger and larger, this approaches zero. Also, the sign convention, electrical potential energy is going to be positive if the two charges are alike, and electrical potential energy is going to be negative if the two charges are unlike. Let's do a sample problem together. The electrical potential energy associated with an electron and a proton is this many joules. What is the distance between these two charges? Well, I need to write down the things I know, and from the problem, all I'm given is the electrical potential energy. I know that I would like to use the formula or the equation for electrical potential energy for a pair of charges. But in order to use this equation, I need to know what the charge is for each of those charges. I can look in a table, and I can easily find that the charge of a proton is plus 1.60 times 10 to the negative 19th, and the charge of an electron is negative that number. This is a very simple problem because I can simply plug these values in and the electric potential energy value in, And I also know my Coulomb constant, so I can plug these values into my equation and solve for R. I can now multiply both sides by R, and then divide both sides by negative 4.35 times 10 to the negative 18th. And when I plug all those numbers in and do the math, I get R equal to 5.29 times 10 to the negative 11th meters. Some advanced ideas. Write the equation for electrical potential energy in a uniform electric field using an integral operation. What would that look like? Or make up your own problem and solve it. Or research some of the earliest observations of electric charge. What cultures have records of experience with electric charge? Or maybe you have some ideas of your own. So look forward to seeing what you come up with, and we'll see you in class.